Okay. Do I want to switch to tablet mode? No. Okay, so this is exam 3. It was 50 minutes long. I also want to let you guys know I had access to the other OChem 2 class that's running right now, and so you guys actually got some of the same questions. I used some of those questions to help pad your exam a little bit. So it's very comparable to what the other classes are doing, or other class. And then you guys are actually going to take the exact same final exam. Okay, so question 1, this was, I actually repeated some of the functional group reaction questions. Miguel asked if you can take the final with me on Zoom on Monday. Yes, just like a regular test, Monday at 11. We'll do it. I know our class starts at 10, but our final exam slot is 11 to 1:30. You know, like just because that's the way the university does it. So 11 o'clock on Monday. So the first couple questions that you got were probably repeats from the previous exam. I gave you guys, I think, 2 or 3 questions that were functional group reactions from the previous one, just to give you guys another shot at that. So an ester is reacted with a Grignard reagent followed by an aqueous acid workup. What functional group would that create? Any ideas?
Would it be a tertiary alcohol?
Yes. So for these, it's really important that if you don't know the answer off the top of your head, just draw out a very basic example of the functional group and maybe work through like a small piece of the mechanism until you have an idea. So you don't even have to, you know, give it full alkyl groups or something, you know, just use OR. And then for the Grignard, you know, just you can use nuke minus, or I guess it's easier to see if we use an alkyl group. So the Grignard is going to attack the carbonyl, and that pushes the electrons up onto the oxygen. And then you have the negative charge on the oxygen, you have your OR group, you have your R group. What happens next? What is the trend that we see with addition to carboxylic acid derivatives? You create this tetrahedral intermediate, and then what happens from there?
Doesn't the oxygen get protonated?
No, not in this situation, especially since we have a Grignard reagent as our reactant right now. We're in base, and the aqueous acid workup won't be added until we've used up all of our Grignard. So what happens next is the double bond reforms and you kick out the alkoxyl group. So remember, the unique thing about carboxylic acid derivatives is that they do have a leaving group. And so when you try to add something through a nucleophilic addition to the carbonyl, you actually end up kicking out that leaving group. And so we have a ketone now with an alkoxyl group, or an alkoxide. So then the interesting thing about Grignards is that they are actually more reactive with ketones than they are with esters, right? That was one of the fun facts that we talked about when we did Grignard reactions with acid derivatives. So the Grignard is going to preferentially react with the ketone again. And that's where we end up with a tertiary alkoxide. Oops, sorry, I forgot my R group there. Which will then get protonated by the aqueous acid workup, because at this point there's nothing more that you could do with a Grignard, and you end up making a tertiary alcohol. So tertiary alcohol is the answer. So I'll do the next one while we have the annotations open. So a nitrile is reacted with a Grignard reagent and then treated with an aqueous acid solution. Oh, the answer is actually not on screen. So is it okay if I clear the drawings from the previous question?
Yes.
Okay, so the options, and I gave you a bunch of them. We have imine, amine, alcohol, aldehyde, enamine, ketone. Does anybody know the answer?
I put enamine, but I feel like that was wrong.
Yeah, it's not an enamine. Wesley put the correct answer in the chat. It is a ketone. So remember the reaction here is we have a nitrile and we react it with a Grignard. Interesting that both of the questions that got picked for my version were about Grignards. It attacks the carbon and then you push the electrons up onto the nitrogen. And you end up here with MgBr as your counter ion. So at this point, the Grignard cannot react with this further because you're not going to end up attacking the carbon and pushing more electrons onto the nitrogen. You're not going to be able to create a -2. So the Grignard is done reacting. Even if there is an excess of it, it's done. And then you add in aqueous acid solution. This will first get protonated. What functional group is this when it gets protonated?
Mine.
I'm not sure if you said the right thing because of the pronunciation. It's an imine. So IMINE. And then in aqueous acid, imines get turned into ketones. So if you react a nitrile with a Grignard reagent and then follow it up with an aqueous acid solution, that is a way to create a ketone. Any questions about this one? A ketone is reacted with a primary amine in the presence of a catalytic amount of acid. What does this form?
An enamine? I mean, on the one with the I. Amine?
This
Yeah.
can make an amine. So a ketone with a primary amine makes an imine. Oops, I tried to draw and I didn't have that open yet. So a primary amine is going to make an imine with a ketone or an aldehyde. If you react a ketone with a secondary amine, you get an enamine. Whoops, I actually saved that. I don't want to save that, but I did. So then the next question actually ends up being a follow-up to that. Satchis was lucky with the way this is formatted. A ketone is reacted with a primary amine. We just did this. That's going to make an imine. So now we've made an imine. And then the resulting compound was reacted with lithium cyanoborohydride. You guys learned this reducing agent in chapter 20. What is this going to make?
Amine?
Can you spell the one that you're saying?
AMINE?
Right, amine.
Oh.
So you have your imine, and then you end up adding hydrogen to it across the double bond. That's going to give you an amine.
Is that reductive amination right there?
Yes. Yeah.
Okay.
This is an example of reductive amination.
Awesome.
Okay. So this gives you an amine. This one was just kind of, you either know it or you don't. The Gabriel synthesis is used to synthesize what?
Primary.
Yeah, primary amines. So remember all of the weird syntheses that you learned in chapter 20, all of them were to make primary amines. Because remember, primary amines are kind of challenging to create just by SN2 chemistry with like ammonia and an alkyl halide, because those tend to go through multiple substitutions. So chapter 20 is like, oh, look at all these cool ways that you can make a primary amine. So that one's kind of a freebie if you noticed that trend in chapter 20. Okay, a ketone heated in concentrated sulfuric acid will form a what? A or an what? So remember the flashcard idea here would be ketone or aldehyde heated in acid. What are we suggesting here?
Alpha, beta, unsaturated.
Right, so this is suggesting an aldol condensation. So that's going to give you an alpha beta unsaturated ketone. Whoops, I didn't close my annotation yet. Okay, there we go. Okay, which compound when reacted in the conditions indicated would give the product below? So this is a very classic type of OCHEM 2 question. You're given a product and you have to figure out which of the reactants would actually be able to give you that. So the first thing that you should do with this is, look at this compound, right? It's a diketone. They are beta to each other. So this is a beta keto ketone, essentially. So the first thing that you could do is kind of weed out the things that won't do this type of chemistry. So for example, we didn't even work with carboxylic acids in these 2 chapters, right? Carboxylic acids do not do this type of chemistry. So cross out number 1 immediately. That's just not an option. Now, the other thing that you can notice is the remaining 5 options. They can kind of be put into 2 categories. We have compounds that contain esters, and then the other 3 have only aldehydes and ketones. So if we were to do a reaction between an enolate and an aldehyde or a ketone, would we end up with a carbonyl in our product? Or would we end up with 2 carbonyls in our product, rather?
No.
When a nucleophile attacks an aldehyde, any nucleophile, do you get left with a ketone?
No.
No. It pushes the electrons up onto the oxygen, right? So the only way that you could do a ketone or an aldehyde would be if one of these carbonyls was a hydroxyl group, and none of them are hydroxyl groups, right? The other thing that you could notice is this is ethoxide. Here is an ethoxy ester. This is kind of suggesting a Claisen type condensation. So that's how I would get rid of options 2, 3, and 4. And I can show you real fast like what you would actually get from that.
I just thought if it was a Claisen condensation, there was going to be an ester group in the final product.
Yeah, this isn't truly a Claisen condensation. It's Claisen-like, I would say. Yeah, in a true Claisen condensation, you would end up with a beta keto ester. So in this case, we would create an enolate here, and it would attack here. That would give us a 5-membered ring because 1, 2, 3, 4, 5 members between the enolate and the carbonyl. Let's number them real fast. All right, so carbon 1 would still have a methyl group coming off of it. Carbon 2 would still have a ketone. Carbon 4 would still have 2 methyl groups, and carbon 5 would have an alkoxide. So this answer is wrong for several reasons. One, we want a 6-membered ring in our product. And 2, this would make an alcohol eventually, and that is not what is in our product. We're looking for a ketone. So that's what would happen with all 3 of those.
Could you work out 3? I just am confused because that would make a 6-member ring.
Right, it would make a 6-membered ring, but it would have an alkoxyl group, just like the one we just did. So if we drew the enolate here and attack there, we would end up with this as our product. Well, and then it would get protonated. So we'd end up with an alcohol, and that's not our product. So let's go through the mechanism with the ester. Well, I'm going to clear all my drawings up faster. So we've crossed out everything except for options 5 and 6. So this is a point where all you'd have to do is count the carbons once you've kind of narrowed it down to what functional groups are going to work. Our product has 9 carbons in it. So our starting material has to have 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8. Not going to work. So the answer is number 6. So I can show you how that works. We're going to have an attack like that. And then our same numbering 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Carbon 1 is still going to have a methyl group. Carbon 2 is still going to have a ketone. Carbon 4 will still have both of those methyl groups. And then carbon 6 is going to have that negative oxygen and the ethoxy group. We reform the double bond, kick out the ethoxy group, and we end up with our product. So this is Claisen-like, because instead of having an enolate made from an ester, we made our enolate from a ketone.
I just am confused on why that aldehyde one would have gotten protonated if there's no hydrogens in the equation.
Well, so even if it doesn't eventually get protonated, like in an aqueous workup, it would never make a ketone, right? It was stuck as an alkoxide. There was no way for it to reform the double bond. Because if you draw out that product again, right now, the reason we were able to reform that double bond is because we had a leaving group. The other thing on this carbon in this structure is a hydrogen. You can't kick out hydride as a leaving group.
Okay, that makes sense.
Yeah, so there's no way to reform that double bond.
Yes. Okay, thank you for explaining that.
Yeah, no problem. Sometimes you just have to find the right words to explain something. So number 6. Okay.
Man, that was a tricky one. I worked through that one for a while.
Yeah, everybody got one like it. So questions 7 and 8 were both ones that had like 4 or more versions. And then I got tired of creating problems like that. So this one says, what is the product of the reaction below? So just like in the previous one, the first thing I would do is weed out some functional group options. So we have an aldehyde. Whoops. I need to turn annotate on if I want to draw. Okay. So we have an aldehyde, and we are in aqueous acid. It's not concentrated acid, and there's no heat. So what type of reaction are we doing?
Would it just be an aldol addition?
Right, yeah, this is an aldol addition. So we're looking for a beta hydroxy aldehyde as our product, right? Because we have an aldehyde in our reactant. So we're still going to end up with an aldehyde in our product. So now you can go through and eliminate everything that's not a beta hydroxy aldehyde as a possible answer, and that'll limit your options severely. So both 1 and 2 are beta hydroxy aldehydes. Carbon number 3 is a beta gamma unsaturated carbonyl. It's not even an alpha beta unsaturated. So that's not even an option for condensation. Carbon number 4 is an alpha beta unsaturated carbonyl. That could be a possible condensation product. Same with number 5. This is also alpha beta and it's unsaturated. This is an alpha hydroxyaldehyde, which is not the product of an aldol addition. So now our options are narrowed to option 1 and 2. What can we do to figure out our answer real fast? Do you see the difference between the two of them?
Like count
One is
them.
one removed and one is directly attached to that hydroxy.
Yeah, or in simpler terms, Sam said that they have different numbers of carbons, right? So one of these is correct, one of these is not. So you could just add up the number of carbons. So this has 8 carbons in it. Our product should have 16 because we used 2 equivalents of it. So we have, sorry, I'll start over here. 6, 12, 13, 14, 15. So that's not correct. So this one has to be it. We have 6 from that benzene, 12, 13, 14, 15, 16. The answer is number 2. So you don't even really have to draw out all the chemistry in order to answer this question. Does that make sense?
Yes, ma'am.
Okay, this one got mixed results. Some people crushed this and some people really struggled. Everybody had a reaction written out like this. There were a couple different possibilities. So when you retake this, you might get a different one. It says use the drop-down menus to fill in the blanks in the following statement describing the Gabriel synthesis. So in the first step of the Gabriel synthesis, you have to look at your options here. So you have some compounds and then you have some actions. So what is the compound that we start with in a Gabriel synthesis?
Phthalimide.
Yeah, you start off with phthalimide. And what happens to it?
It gets deprotonated.
Yeah, it gets deprotonated.
Yep.
Yeah. By what? Which of these options would be used?
KOH.
ETOH.
All right, so it's going to be
Okay.
KOH. Oh, I just saw Matthew's message. I don't know if you're still here, Matthew, but thank you. I'll post the video later so you can get the rest of the material. Okay, so then a or an blank is added and a or an occurs. So you have to kind of look at the blanks to see, you know, what the hell is supposed to go in here. So we have a compound and a type of reaction occurs. So what is added next after you've deprotonated phthalimide?
Is it a tertiary amine?
Not a tertiary, well, it's not an amine at all, but definitely not a tertiary one.
Is it alcohol?
No,
Isn't it a primary alkyl halide?
right. Yeah, we're going to do an SN2 reaction with a primary alkyl halide, so nucleophilic substitution. So then in the last step of the Gabriel synthesis, there are 3 things added. So one of them is ethanol. I gave that to you. Which of these is added to the reaction? We have hydrazine, nitrous acid, sodium azide, sodium azonide, or aqueous acid.
Hydrazine.
Right, hydrazine is added. And what about the temperature?
Reflux.
Right. Okay, and then the final product is a what?
Primary amine.
Right. Okay, number 10 has more functional group questions. So the condensation of a diester to form a cyclic beta ketoester is specifically known as what? What reaction makes a cyclic beta ketoester?
Is it the Deichmann condensation?
Right, yeah. So remember, beta ketoester is the product of a Claisen condensation, but when it's, two esters, I'm not an annotate, when it's two esters in one molecule and they create a cyclic structure, it's called a Deichmann condensation. So Deichmann. The replacement of a diazo group from an arene diazonium salt by reaction with a copper 1 salt is known as a what?
Sandmeyer?
Mm-hmm. Yep, this is a Sandmeyer reaction. An acid chloride is reacted with sodium azide and then heated to produce a primary amine and carbon dioxide. This reaction is known as what?
Not the Curtis rearrangement?
The Curtis rearrangement?
Yeah.
Yes, I believe so. I'm brain farting right now. It's one of the rearrangements. Yeah, I believe that's Curtis. Question 13, a secondary amine is likely to be a stronger base than a primary amine. Is this true or false? So we're talking about the difference between, whoops, let's draw the hydrogen there. The difference between dimethyl amine and methyl amine. Does anybody know?
True.
Yeah, this is true. So alkyl groups are electron donating. So you are increasing the electron density of the nitrogen. That makes it a better base. It's true. In a crossed aldol reaction, it's better to use a strong base to create the enolate than to use a weak base.
Is that one true also?
Yeah, this is also true. The reason being that typically you take compound A and you want to fully deprotonate it to create your enolate before you add compound B. Otherwise, you're going to end up with a couple different products potentially. So you want to completely deprotonate your first compound. And so using a strong base will get that done. In a coupling reaction of an arene diazonium salt with a phenol derivative, the reaction will proceed more rapidly with the phenol than with its conjugate base, phenoxide.
I'm not sure.
So this one actually pulls information from electrophilic aromatic substitution also. One of the things that we learn is that being deprotonated increases the electron density within the benzene ring. So it's going to make it more reactive. So this says the reaction will proceed more rapidly with the phenol than with its conjugate base. That is false. Okay, and then last true false question. In acidic conditions, the nucleophile which would be formed and participate in an aldol reaction is an enol. Is this true or false? So remember, we have two different versions of deprotonated carbonyl nucleophiles. We have the enol form and we have the enolate form. Which one exists in acid?
Wouldn't it be the an acidic?
Yeah, so this is the version that exists in acidic conditions. So this is true. Okay, question 17. Identify the missing reagent X that would complete the transformation below. So in the first step, we have sodium nitrite and hydrochloric acid. What are we doing here? This is the same as doing a reaction with what?
Are you just making the diet? Was it the diet salt?
Yeah, the arene diazonium. So sodium nitrite and HCl together is essentially the same idea as reacting with nitrous acid, right? So this is going to turn this into the diazonium, right? So then if we somehow turn the diazonium into a nitrile, what reagent is going to do that?
Isn't it CuCN?
Right, yeah, this is an example of the Sandmeyer reaction. So remember, the Sandmeyer is done with cyanide, bromine, and chlorine, all with the copper 1 salt. So none of these other things are going to work. Question 18, identify the product of the reaction below. So this actually originally started out as a much harder question, and I tamed it down to this. So we have a secondary amine, and we're going to first react with formaldehyde and hydrochloric acid, and then we're going to follow it by reacting with a ketone, a dicarbonyl compound. What are we doing?
A manic reaction?
Yeah, this is setting up a manic reaction. So if you were in, maybe I said this in office hours one day, but I feel like I also did this in lecture. The kind of easy approach to a manic reaction is to think, A plus B plus C. So we have an A plus B plus C formula where we're going to add on 1 carbon to the nitrogen. So that's our A plus B. And then we create a bond to our enolate carbon. That would be C. So we are looking for a situation where there is a single carbon between the nitrogen and the enolate. So this would be the product after step 2. This is the product of our manic reaction. But what happens in step 3? We have H3O plus and heat. What's going to happen to the ester at that point?
Doesn't it get eliminated?
Yeah, so it's going to get turned into an acid, and then we'll have a beta keto acid, which decarboxylates in heat. So we are looking for the decarboxylation product. So imagine just kind of crossing this out, and you end up with M. Yeah, and if you're, going through these and you're trying to just eliminate options just based on like the number of carbons in the structure, L would be something you could cross out pretty quickly because it didn't even use the formaldehyde. It just somehow attached nitrogen to an enolate carbon. Option O kind of just disobeyed the rules of chemistry entirely. It made the enolate on the least acidic proton, or at least acidic alpha carbon here. So that's not going to happen. So those are both out. And then P, I just drew that like as an option. It doesn't even make sense. So N would actually form after step 2, but step 3 turns N into M. So answer is M. The quaternary ammonium compound below, which is on the left, is treated with potassium hydroxide at 150 degrees C. which compound will be the main product of this reaction? What type of reaction are we doing? We have a quaternary ammonium, and we're reacting it with potassium hydroxide at 150 degrees Celsius. What type of reaction is this?
Is it the Hoffman?
Right, this is the Hoffman elimination. So all of these show you that you end up with an amine and an alkene. The Hoffman elimination makes which alkene? Does it make the most substituted or the least substituted?
Least.
Right, it makes the least substituted. So what I would do is look at the least substituted alkene here and make sure that it makes sense with the number of carbons and where the beta protons would be. So W has the least substituted alkene. So if we imagine a line here, that does look like our original product. And the way that this would be formed would be if we pulled off this proton. So that actually makes sense, and W is actually the answer. There are a couple things here that well, there's only one actually that just couldn't be made at all, and that's why that's just not going to be made. That didn't actually break any bonds to the nitrogen other than removing one of the methyl groups, which doesn't make sense at all. So the answer is W. Oops. Okay, cyclohexanone can undergo a self-aldol condensation. Identify the product that would form in this reaction. So what I would do if I were you is go through this and again, eliminate all the things that are not the product of an aldol condensation, right? So what is the product of an aldol condensation again?
Alpha, beta, unsaturated.
Right, an alpha beta unsaturated carbonyl. So number one is an alpha beta unsaturated carbonyl. So we can leave that as an option. Number two is not. Number three is a beta gamma unsaturated, so that won't count. Number four is also alpha beta, and number five is alpha beta. So from here, now you want to look at the connectivity. Which carbon, if we're looking at cyclohexanone, which carbon is going to be attached to the other equivalent of cyclohexanone? Like where in relation to the carbonyl is it? Which carbon does the chemistry happen on?
I want to say alpha, but I don't know.
Yeah, no, you're right. It's the alpha carbon. The reason I'm asking is that this one has it connected at the beta carbon. That's not an option.
Okay.
So now we're between compound 1 and compound 5. So here, if you understand how this reaction actually occurred, you can pretty quickly eliminate option 1 because even though this is an alpha beta unsaturated carbonyl and the other cyclohexane group did end up on the alpha carbon, the elimination did not happen in the correct place. So think about your addition product. It would look like this, right? And then we're going to pull off this proton and eliminate across here. So we end up with a double bond here, right? The double bond should be between the two equivalents of the molecule. If you look at option number 1, that double bond formed on one equivalent of the molecule, right? It is not involving the second one. So that is not correct connectivity overall. Does that make sense?
Yes, definitely.
You can also, shorthand this reaction really quickly. I kind of mentioned this the other day, but, draw your carbonyl overlapping with your alpha carbon and then find the product that looks like that. So put your carbonyl oxygen of the thing that you're going to attack on top of the alpha carbon and just draw the rest of the structure out, and you end up with something that looks like the product. That usually works if you understand how the chemistry actually happens. Sometimes I get students who don't understand how the chemistry works, and then they try to do that and it just doesn't work out for them. Okay, provide the IUPAC name of the compound below. This crushed a lot of people. So when you're doing IUPAC naming, all the same rules all the time, right? First, you find the longest carbon chain. What is the longest carbon chain?
Butane.
Yeah.
Yeah, so we have a 4-carbon chain. So what is a 4-carbon amine called?
It's butanamine.
Right, yeah. So butanamine, however you want to say it. The other thing that we have to indicate is that the amine is on carbon number 1, because you can also have 2 butanamine. All right, so 1 butanamine. And then our other substitution is on the nitrogen. So how do we indicate that?
N-ethyl.
Right. So this would be called N-ethyl. That's a long dash between those. 1 butanamine. Does that make sense? Okay. Also, for the record, when you guys redo these questions, I'm going to pull all the ones that we are working on right now. So you won't be able to take any of these answers into that. So just keep that in mind. Don't type out the answers that we're doing right now or pick the same choices, because then I'll know that that's what you did. I'm not going to reuse them. Okay, so N-ethyl, whoops, 1 butanamine. Okay, for this one, you had to remember what the most important group is. So between a amine and a hydroxyl group, what is the priority?
The hydroxyl group.
Right, so we're going to name this molecule like it's an alcohol with an amine substituent. So let's name this alcohol. We want to start numbering over here because that's closer to our alcohol substituent. So what is the bulk of the name of this alcohol?
Something. I don't know.
Is it hexanol?
Yeah, it's hexanol. And then we have to indicate where the alcohol is. So we have 3-hexanol. And then what else do we have to say? What is the substituent name for an amine?
Amino.
Right. So 1 amino, 3-hexanol. I also plugged in 1 amino hexane 3-all as a correct answer. So if you did it that way, you got the answer correct as well. Both are correct. Okay, any questions about this?
No.
Okay. Clear all drawings. Okay, so I want to give you guys a second to look at this one. I need to send an email. I'm supposed to meet with someone at 11, but we're not gonna quite be done at 11, so I just want to let them know. So just go ahead and think about this one for a second. So identify the product of this series of reactions below. Does anybody know what type of reaction we're setting up here? Okay, let's. What?
Some form of a Michael?
Yeah, so this is going to be a Michael edition, and it's also kind of combined with a storic enamine synthesis.
Yeah, okay.
Yeah, so the first step has a secondary amine, it's dimethylamine, and we also have hydrochloric acid and a ketone. So we're starting off by making an enamine. So after step 1, we have an enamine, and it is going to react with our alpha beta unsaturated system here. Where is the enamine going to attack? Is it going to attack at the alpha carbon, the beta carbon, or the carbonyl carbon?
Isn't it the beta carbon?
Right, it's the beta carbon. Right, all things attack at the beta carbon of an alpha beta unsaturated system, except for Grignards and alkylithiates. So it's going to bring its electrons down, push those out. Let me erase the beta, alpha, and C there. And then we attack here. I'm going to go ahead and just put the electrons here so that it's easier for us. So this is a Michael addition. So, and then we're following it up with water. So we're going to end up getting rid of the aminium ion that we're about to form. So we're going to end up with a ketone. So what I would do right now, if I were you, is eliminate the obvious options. So if I'm doing a Michael addition, I know that this double bond is going to be gone. And I know that I'm creating a bond from this carbon to this carbon, right? So I would go through and eliminate all the things that are clearly not doing this chemistry. Like option C has an attack at the carbonyl carbon. Not going to work that way. Compound A has an attack at the alpha carbon, and it also dropped the methyl group that's actually on the starting material. So option A is not valid. Option R is actually the answer, so we'll come back to that. Option B has an attachment at the beta carbon, but it dropped the methyl carbon that's on our starting product, acetophenone, our starting material. So that guy's gone. Option O has the correct connectivity, but kept the double bond. That's not how a Michael addition works. And then option N made like an amide or something and then attacked, I don't know, I just made that up because I figured like somebody's gonna think that's what happened. I don't know. So even just by doing that, we narrowed it down to the only possible correct option. Another good starting place would have been counting carbons. That would have eliminated option A, option B, and option N. And you'd be left with COR. So that would have been a good way to narrow it down as well, if you weren't exactly sure what was happening. Does that make sense?
Mm-hmm.
Okay. Clear all that. So the correct answer was R. Okay. Identify the product of the series of reactions below. So we're starting off with a ketone and an ester, and we have sodium methoxide and methanol. This is very, very similar to that first reaction we did where I said it was Claisen-like, but not actually Claisen. So you end up creating an enolate here. It attacks the ester. And that's going to give us a 1, 2, 3, 4, 5, 6-membered ring. 1, 2. There's going to be a ketone here. And then here we're going to have an alkoxide and the methoxy group. It's going to kick that out. And so we end up here after step 1. So before we move on to step 2, I would go ahead and eliminate all the options that don't even remotely look like this, and that actually gets you to the answer even without doing step 2. So Q is gone, R is gone because it has a hydroxyl group and an ester when we need 2 ketones, and they're not even positioned correctly. T and U both have 5-membered rings, so those are not going to work. S is actually the answer. So you take a look at the next 2 steps, that's sodium borohydride and water. That's going to reduce both of the ketones to alcohols. And so S ends up being the answer. For some reason, when I'm doing this preview right now, it made the first answer the correct one like 90% of the time. It's supposed to mix them up. Does that logic make sense? You guys understand where that came from?
Yes.
Which reaction conditions will result in the transformation below? This is a very similar reaction to the one that we looked at earlier. We turn an amino group into a bromine on a benzene ring. There's only one way that you guys know how to do this, and that would be through a Sandmeyer reaction. So the first thing that I would do is go through and eliminate all the options that don't start with nitrous acid. And that will get you to the answer immediately. So this is nitric acid. That's not an answer. This is bromination. That would put a bromine here. That's not what we're trying to do. HCl, sodium nitrite, water. This would give you nitrous acid. And then there's the bottom one just has aqueous acid. So even just that gives you the correct answer. If all you could remember about Sandmeyer was the C1, copper 1 bromide, that would narrow it down to options 3 and 4. And then you might be able to narrow it down if you compared aqueous acid to this. So always start by narrowing down your options. A compound, which is compound 1, is reacted with LDA. Then compound 2 is slowly added to create one single product, which is the product identified in the box. Identify which compound must be compound 1 and which must be compound 2 in order to create the indicated product. First of all, does this question make sense?
Yes. It was nice how you had them at compound 1, you had only a few of the letters, and then compound 2, you had the other half, I think, right?
Oh, I hope not. No, I think I put them all.
Yeah, mine had all the letters for like each.
Never mind.
Yeah, no, that would have been too friendly. That would have been too nice. So the first thing that I would do is think about how this connection is made. So we ended up with a beta keto aldehyde of some sort. So what does that tell us about what the compound that we're attacking? Can this be a reaction between 2 aldehydes, or an aldehyde and a ketone, or 2 ketones? Would that ever make this?
No, would it not?
No, it can't. So if you have an aldehyde plus a ketone, or any combination of aldehyde and aldehyde, or ketone and ketone, you have 2 options. You could end up with a beta hydroxy carbonyl, or you could end up with an alpha beta unsaturated carbonyl. Those are your 2 options, and that's not what we ended up with. So for compound 2, that actually narrows it down really quickly. For compound 2, there's only one thing that it could be, right? We can also see like this can't be a Michael addition because look at the number of carbons between the two carbonyls. That eliminates option C, and by what we just said, we eliminated O, H, M, and G. So the correct answer for compound 2 has to be R, just because of the functional groups that are left over. So then from here, all you have to do is decide what attacked compound R, and that makes your life a lot easier than trying to like sit here and go, okay, reacting O and R gives me this, O and G gives me this, O and C, O and H, O and M. I hope that's not what anybody did. You definitely want to like puzzle your way to where you have fewer options. So compound R has 1, 2, 3, 4 carbons. So that's 1, 2, 3, 4. That means that compound 1 has to have 3 carbons and an aldehyde. So what is the correct answer for compound 1?
M.
M.
And which one was the attacking one? The first one?
Yeah, so compound 1 gets deprotonated with LDA. It makes the enolate right here. And we can actually see that because that's the bond that's created here. It's made from the alpha carbon to the carbonyl carbon of R. So when that attack first happens, oh, that's horrible. We end up with this, and then we kick out chloride, and that's how we end up with our product.
Sweet.
Okay. Compound 27, or question 27, sorry, not compound, that's weird. An amide with the chemical formula C10H19NO is reacted with sodium azide and then heated to 200 degrees. What is the chemical formula of the main organic product? What are we doing? What
Is it
reaction?
eliminating the NO group? Or just the oxygen in it?
Not just the oxygen. So this is a reaction that takes an amide and turns it into an amine where the entire carbonyl gets removed. So we're just looking for a formula that's 1 carbon and 1 oxygen less.
So
1 carbon and 1 oxygen left.
So which answer does that?
the first one.
Right. So the correct answer is the first one. Oops. And that was that test.
It is.
Are there any questions? I do have to go pretty quickly because I was supposed to meet with someone about 10 minutes ago. But do we have any questions?
I was just gonna ask, like, is there still hope for this class? Like, I know we have the final, and I'm like right on the edge there, you know, but I don't know. I've been trying my hardest.
Me too.
Yeah, do the extra credit that I'm going to put out and make sure that you study for the final exam. I think there's hope for a lot of people. If you're kind of borderline, then yeah, there's hope for you. You just have to make sure that you come prepared and that you do this extra credit, do the extra credit homeworks that are still open. Okay. Make sure that you do everything that you can.
Alrighty, thank you.
I would work really hard this weekend.
Oh, I am.
Miguel asked what code are we using on Monday. We'll just use the Monday lecture code. And then Wesley asked, what do I suggest that you study for the final? The final exam covers OCHEM 2 and OCHEM 1. So it's all on there. You need to do practice problems. I would review your old quizzes, review your old exams. I would go ahead and do the extra credit that I'll open up for you guys later. Like I would do that as part of your final exam prep because you're going to end up seeing a lot of similar questions. I will say that the questions for the final exam are worded a little differently than how my questions are normally worded because I made this with another faculty member. And so we kind of had to serve both his class and mine. But the questions I think they ask really similar ideas.
Oh, and so it's not ACS either?
No, it's meant to kind of look like the ACS exam.
Okay.
Chase, I don't have a practice exam. I'll see if that other faculty member does. I did put up that PowerPoint that had a lot of questions that covers a lot of the reactions that are on there.
Okay, thank you.
Mm-hmm. Okay. Anything else, guys?
Thank you. This was helpful.
Okay, I'm glad.
Oh, yes. Last thing. Is there any way we can view our test 1 and test 2 or no?
You should be able to view it.
Oh, okay. Awesome. I'll go look at that.
Yeah, if you can't, let me know, but you should be able to view it. Yeah.
Sweet. Thank you so much, Dr. V, for the help this year, everything. Appreciate it.
Oh, no problem. Thanks.
Have a good one.
You too. I'll see some of you guys on Monday.